Hello, everyone. Thank you for joining us this afternoon for this competitive advantage talk presented by Kager, also known as the Craft Analytics Group. My name is Ben Seeley, and I'm an MBA student here at MIT Sloan. It's my pleasure to introduce this presentation today titled Sports Schedule Optimization. Please join me in welcoming our speaker, Dr. Chris Grower, co-founder and chief product officer at FastBreak AI, to the stage.
Thanks. Thanks, Ben. Thanks for everyone for coming out today for one of the later sessions here. Hopefully it'll be interesting to you and maybe one of the more technical sessions, and I look forward to your questions at the end. So let me start by talking a little bit about our company. So we're called FastBreak AI. We were founded in 2022. And it's amazing for me to see that we're up to now 41 full-time employees through a series of acquisitions and focusing on professional scheduling and youth sports. And the focus of the company is really to take the expertise that we've developed in working on other complex optimization problems in the world of routing, scheduling, and so on, and democratize that to the world in sports. So you can see a number of leagues that we work with here and the number of people, and it's a great group of people that we work with. Optimal Planning Solutions, Rick Stone, he worked with the NFL for about 20 years as part of his company, and we recently acquired a company called Barcelogic that was in Spain, and they worked with many of the European soccer leagues and FIFA and so on. So in some ways, I sort of wanted this to be the title of the talk, right? How hard can it be, right? So a little story here about how I got into all this. I just finished grad school at the University of Maryland, and I was working at Oak Ridge National Lab. And my job there was to take these jobs that are coming into these supercomputers and figure out where should these jobs go on the computer at any given time. And I thought, oh, this is a hard problem. We have hundreds of jobs coming in, and my work in grad school had been working on very large vehicle routing problems. And so it turns out my sister-in-law at the time was the soccer coach at the University of Tennessee, and she comes to me and she says, Chris, we're having lots of problems with our schedule. We have 4 away games in a row. No other team has 2. I may be getting some of the details wrong. But the fact was that they were, doing the schedule by hand, and it was very unfair in many ways. And so she said, Chris, maybe you can look at this as a math problem and see what you can do. So starting at the kitchen table and messing around with Excel and things like that, I was like, God, this is really challenging. This is a lot harder than I expected it to be. So I thought I'd first begin by describing how hard is this problem. So one way we often talk about the complexity of a problem is in how many possible solutions there are. But that often doesn't tell the whole story. So if I give anyone in this room a list of 1,000 numbers and I ask you to sort it, well, you're going to be angry at me for asking you to do something so mindless, but you're going to get the right answer and you can do it pretty quickly, even though there are apparently 1,000 factorial, which is 10 to the 2,567 ways to do this, right? So a lot of possible solutions, but in some sense it's easy, right? So now let's up the ramp of complexity to something that a lot of people in here may know, probably the most famous optimization problem that we all learn on, the traveling salesman problem. So that first picture there of the United States, that's actually the shortest path you can take to visit all 48 capital cities in the US and return to where you started. And so this was, I think, in the mid-60s that they first used a computer to solve this problem. And people thought, oh my gosh, we can now solve all these difficult discrete optimization problems to optimality. This is going to be great, all the things we're going to be able to solve. Well, over time, this has kind of been the problem that the commercial solvers and a lot of research has gone into, and it turns out we're very, very good at a problem like the TSP. So this picture of the Mona Lisa, I don't know how good the resolution is. Maybe in the front row you can actually see that this is a Mona Lisa that's made up of 100,000 different points, and there's a line connecting every point. So if you started in the bottom left of that picture, followed 100,000 edges, you'd end up back where you started. And the amazing thing about that path is, let me cheat real quick. That path is 5.7 million units long, and however they're measuring distance, and we know that that tour is within 107 units, or 0.002% of the optimal, right? So there's $1,000 if you can actually prove it's optimal. It's probably the hardest way you can ever choose to make $1,000. But for all practical purposes, even though the TSP is an NP-hard problem, it's solved to optimality. All right, well, let's make the problem a little bit harder. So this is a problem near and dear to my heart called the vehicle routing problem. And in this problem, we're given a set of vehicles, maybe like UPS, right? So maybe you're given a set of 10, 15 vehicles, and they say, all right, your job is to go visit 300 customers, drop off some packages, pick things up, and minimize your cost. And cost is usually measured in terms of the total distance. Well, when I was in school, we were working on problems with maybe between 50, 100, 200, up to maybe 1,000 locations. And about 5 years ago, we were able to prove, not me, but the community, was able to prove the optimal solutions for problems that have up to 200 locations or so. So I wouldn't say that this problem is solved in the sense that the TSP is solved, but for practically sized problems, we're very, very good at this. And these problems obviously occur everywhere in industry, right? All right, so we've gone from sorting a list of numbers, really easy but huge solution space. The TSP we've solved as humans, and the vehicle routing problem, still a lot of work needs to be done. Now let's go to sort of an idealized version of a sports scheduling problem called the traveling tournament problem. So this, to give credit where credit is due, this problem was actually conceived by one of my coworkers, Kelly Easton. This was her dissertation at Georgia Tech, I think back in 2001 or 2002. She might be mad at me for saying that. But what they did is they decided, let's make an idealized version of the MLB scheduling problem where we've got some number of teams, and I think they made it be even to make the math work out nice. So imagine you've got 16 teams, you have to play a double round robin, and you can't have a 3-game homestand, and you can't have a 3-game road trip, and what you want to do is minimize the total distance traveled. Okay, so conceptually we can describe that problem to our kids, and surely with 16 teams, that's got to be easier than, you know, solving this Mona Lisa TSP to optimality. Well, after 900 different research papers, the answer is actually no, as far as we know. So there are still instances with only 16 teams where this traveling tournament problem, we don't know the optimal solution. And when we get to something of the size of, say, 30 teams, which puts us in the realm of like Major League Baseball, the gap is 50%. So maybe our solutions are very good, maybe they're not, but the thing is that the math has not been able to tell us yet how good we are at that problem. So in some ways, I wish this would have been the title of the talk, but hopefully now as I continue to talk about sports scheduling, you're convinced that, at least from the research from the people in the world and academia, that this is a very difficult problem. All right, well, it's a hard problem, but sports are played every day. We see the ESPN ticker, and we're having a conference about sports, so how are schedules made? So back in the day before computers, we scheduled by hand. So the picture at the bottom there's a 30 for 30 on them. It's called Henry and Holly Stevenson. They made the Major League Baseball schedule for several decades, maybe 20, 30 years, mostly by hand, but they did have some very early, support from mainframes and things like that, whatever was available in the early 80s. And this was in the days of not having much, I'm not sure any interleague play, right? So then around 2000, when interleague play came in, we went from kind of having two separate 15-team problems to one giant 30-team problem that was now linked, and the computers started to win. And so we divide the universe of problems at the professional level into what we call these day-based leagues. Would be something like the NBA, the NHL, the AHL, where teams are playing every day of the week, potentially, and not strange, but different types of rest patterns. So you may have a back-to-back, you may rest 2 days, you may rest 1 day and then play again. Whereas if you go to something like a college basketball league or the NFL, in college basketball you have a midweek round and then a weekend round, and then the NFL you're playing once a week, and it could be on Monday, Thursday, or even Wednesday this year on Christmas. And so those we call these interlocking leagues. And the NFL made for years their schedule by hand. There's actually some stories out there about this cork board that I've seen in their office where they have these hang tags and they place their what was then 256 games. And it's much more difficult because there's very little flexibility. Once you get to the point where you need to move one of these hang tags to put a new game on TV or break up maybe 4 away games in a row, you've destroyed a huge part of that schedule. So it's still possible to solve these interlocking leagues by hand, but it becomes very difficult. You have one schedule, and fixing any kind of issue that you have in that schedule can be very, very difficult. Okay, so I talked a little bit about this before, scheduling research. Well, it turns out that that Google search at the top there for sports scheduling in quotes, there's about 1,600 research papers that have been published in the community. And then on top of that, of course, there's people from industry like myself that will never publish what we do. And there was actually in 2021, there was a competition in Belgium on timetabling. They have a timetabling competition every year. And this year they chose, in 2021 during COVID, they chose sports. And so there were teams, I think there was maybe 12 to 15 teams that worked on a set of benchmark problems that they had developed. And they were kind of like the traveling tournament problem, but expanded, right? So then they were looking at minimizing the total number of times team would have away, or minimizing the total times to have home, minimizing distance, things like that. And even though that they were working on these sort of small, what we would consider idealized and not realistic versions of the problem, it turns out that they still were very, very difficult, and there was really what I would say was no breakthroughs in terms of the approaches that they would take. So really, the teams that performed the best in these competitions were the ones that put the most computing effort into it, right? And so we're talking, not like your gaming PC at home, we're talking, thousands of PCs at once on a cluster at a school in Europe and things like that. So, and similarly with the NFL, for example, there's a story that comes out usually every year to talk about the immense amount of computing that they put forth on their problem every year. So it's hard, I keep emphasizing that it's hard, but now let's talk about what makes it even harder, right? So you take something like the traveling salesman problem, and our objective function, the thing that we're trying to minimize, is crystal clear. It's the distance, right? Or a vehicle routing problem, first minimize the number of vehicles that you're using and then minimize the total distance. Well, when we get to sports, if we're doing the Major League Baseball schedule, they don't come to us and say, okay, Chris, all we care about is minimizing the total distance and making sure that no one has a 4-game trip. Like, that doesn't tell any part of the story. And so when we think about an optimization problem, we have what we call an objective function, which is the thing that we're trying to minimize. So when it comes to sports scheduling, and we've created this optimization problem that we're solving, what is the objective function? Well, it depends on who you ask, right? If we go and we ask a coach, the coach may care about consistent home-away patterns, player health, giving them a schedule that he thinks or she thinks will help them win the most games. If you talk to the media partners or the TV networks that are working with the leagues and broadcasting these games, well, they want something very different, right? They want to see the top teams on the top time slots every single week, and they don't really care about a lot of the rest of the schedule and what happens to the teams that may not be in TV because it doesn't affect their bottom line. Well, other players in this ecosystem of scheduling are the owners and the venues, right? So the owners of the venues, well, they know that they're going to get, in the case of an NHL season, they know they're going to get their 41 games, but if they have a chance to book a Taylor Swift concert and hold on to that date, I'm pretty sure that's what they're going to do, right? So they know that they're going to get their 41 games, and they have an idea of what days of the week that they want to play on, and they want to maximize the games that are on the weekend if they don't have a concert so they can maximize ticket sales, right? So if we think about what our objective function is in these sports scheduling problems, it's very complex, it's very rich, and the people, these different stakeholders often, are not even in the same room talking the same language when it comes to things about the schedule. So on the one hand, we have this very difficult math problem, right, going down from the TSP to the VRP to this traveling tournament problem. But then, to make matters worse, or better in the case of a company that specializes in this, the thing that we're optimizing is also very, very difficult to define. So how do we do it with math? So I've been to a bunch of talks here. I haven't seen an equation yet, so here's our first equation of the conference, for me at least. So the classic way that you work on these problems is something called integer programming, right? And this was when I was working on this, in Excel 15 years ago for my sister-in-law. This is what I did. It's kind of the natural approach to anyone who works in this area. And so fundamentally, we have one variable that describes, is a game going to be played on a date? So we have x, I, j, t is going to be 1 if team I hosts team j on some date t. And it turns out that even if you're not that clever, you can write many, many different aspects or properties of your schedule in terms of that variable. There's a lot of work in academia on other formulations where you introduce new variables to describe maybe what a road trip is or unequal rest and things like that. But for the most part, if you just use this very naive formulation, you could solve maybe a 12-team problem to optimality on your laptop. And as the computing power has increased over the last 15 years and the solvers have gotten better, these sorts of small leagues have become really in the realm of personal computing, I would say. But once you start moving up to, say, a reasonable sized NCAA conference or any size professional league with 16, 20, 30 teams, nothing is going to work out of the box, and you're going to have to be very creative to know how to use these very powerful optimization solvers to work on these problems. One nice thing that we saw, like when I was talking about the TSP, is sometimes they'll let you know with the math behind the scenes how far you are from optimal. So we've got some objective function that is this mixture of all these things that we're optimizing, and with the integer programming, we may know, hey, your solution score is 1,000, and I don't know if there's a solution that's better than that, but if there is, it's only better by maybe 10%. So that can be something very useful. If you're working on one of these problems, you can say, all right, I'm within 10%, I give up, I quit, that's good enough. And I think one of the biggest issues with this approach is as your league grows from a toy team league of 6 teams to maybe 12 teams and so on, the scalability really starts to suffer because these problems truly are exponentially difficult as they get larger. Okay, so other approaches. This animation here is the traveling salesman problem with a heuristic. So a heuristic basically means you start with some feasible solution. In our case, that would mean all the games are scheduled, and we make small local improvements to that solution in an attempt to improve it. And so for something like the TSP, that works very, very well. Like that solution that I showed you, that was discovered by a group in Japan using very, very clever heuristics. One issue with this is that you get stuck, right? So you'll get a solution, and I don't know if this solution is actually optimal, but you'll get to a point where you try all these fancy moves that you have to go from one solution to another, or one schedule to another, and you can't improve it, and you're stuck, and you need to basically destroy half of that solution before you can improve anymore. And the other thing is there's no notion of optimality. Like the math here is really fairly simple, and so whereas opposed with the integer programming approach, we may know that we're within 10% of optimal. With heuristics, we really have no idea if we're close to optimal, if we're within 50% of optimal, and so on. All right, so how do we do it? Well, I'll talk a little bit about our approach, and then I'll take some questions. So one of the key things that we sort of decided early on as a company is that the user interface to look at schedules, to analyze schedules, and to write the rules or constraints needs to be very tightly integrated. So like, for example, here, there's a picture of a road trip for a team. What does it look like on the map? How many time zones are they crossing? What is the optimal distance of that trip? And all sorts of metrics that you would want to see about that trip. So then you're looking at this in the context of your optimization, and you think, well, if this is the worst thing about my schedule, can I live with it, or do I really need to fix that? Other things that we show are constraint violations. So a professional league these days may have, I don't know, I would say maybe up to 200 different constraints that they have in the system, and they all have sort of an importance that's attached to them. And so what we do here is we show you, here's a violation of avoiding 3 games in 5 days. It turns out this schedule had 74 of them. And is that bad? Do you care about it? When you see that you have 74, do you really care about eliminating them? Or is there something else in the schedule that's worse that you want to try to focus on? So we give the user all these different knobs to tune to focus on different aspects of the schedule. And then there's some mundane stuff too. The data management of the teams, right? So we have a system where the users, the teams and the venues can log in to give us the venue availability. Because if we get to a point where we've made a schedule for a large league and we have a home game when a team has, we'll go back to the Taylor Swift concert. I'm pretty sure Taylor Swift is not going to move that concert. And so now we have to fix that. And that may come at the expense of moving games for 10 other teams or something like that. So it's very critical to get this data right, because one mistake can truly be catastrophic in the home stretch of the process. And then finally, metrics. What is the total distance traveled by each team? And I didn't really talk about this too much, but another huge part of scheduling at the professional level is fairness, right? And so for every metric that we show, whether it's total distance, how many undesirable home-away patterns they have, we show, if you're the worst in some category, you're red. If you're the best, you're blue. And in general, you want to see not a lot of red and blue and a lot of white. So amazingly enough, that's 7 seconds to go. So I'm just in time to start 5 minutes worth of questions. And maybe we'll get into some of these topics as we go to questions, but I want to give people a chance to answer or to ask.
Yeah, just curious, how much of a wrench does it put in the plan if like an expansion team gets announced, or is that a fix that's really easy when it comes to scheduling?
Nothing's easy. Nothing's easy. Well, yeah, I mean, so that if an expansion teams come to the league, the first thing you have to do is decide who they're going to play, right? So if the NBA added one or two teams, well, are they going to stay at 82 games? Probably so, but what are those 82 games? And then the travel patterns may change. Like last year, the NHL, as you all know, had a team move from Arizona to Utah. Well, that didn't really have a huge impact on any candidate schedules to that point because for the purposes of travel, Arizona and Utah were kind of the same, right? But if Arizona had moved to Knoxville, Tennessee, where I live, there would have been a huge impact. So I think as long as it's very important to have all the information up front, and if there are no surprises during the process, then obviously everything runs much more smoothly.
Hi there. I had a question about does the concept of like disoptimizations, introducing disoptimizations into the schedule, is that incorporated? The example would be if one team ends up with a back-to-back, the team that they're playing against must have a back-to-back as well, something like that.
Yeah, so there is a concept of sort of unequal rest that comes up a lot in leagues like the NBA, the NHL, college basketball too has been focusing on that a lot more. And yeah, I mean, sometimes you have to make tough decisions. Like sometimes, am I willing to make one team's schedule a little bit worse from their perspective to make it more fair? And that's a difficult question to answer if that's the right thing to do. But fairness, as teams, really from college all the way up to pros, they're becoming more and more analytical about the schedule. And you can go on Reddit and read people that are criticizing everything that's done in a schedule. Fairness is becoming more and more of a huge thing to the point where sometimes maybe you're willing to accept like a negative aspect of a schedule for a team if it helps the overall health of the schedule in terms of fairness.
Hi, thank you so much. I was curious if you could go over how you guys are integrating Gen AI, particularly LLMs, and then also what you think the impact of quantum computing could have on this.
I figured that question would probably come up. All I'll say is that I do not own any stock in D-Wave or Rigetti computing. So one thing that we're doing, I didn't talk about this, but the machine learning that we're doing in the product to this point is we have 3 leagues that have gone and used the system to sort of rate historical trips on a scale of 1 to 10. And then that incorporates a lot of things. It incorporates the routing of the trip, the composition of the trip, the rest pattern on the trip, the time zones, things like that, so that then we can write a constraint that says, hey, I don't want a trip that's worse than 5.6 or something like that. So when it comes to LLMs, one of the most difficult things for a user in the system, like right now I think we have 146 constraint types behind the scenes, and you have to either be someone who works at the company or a super user to know if I have a rule in my head about a schedule, which constraint am I going to pick for that? So one thing that we've been experimenting with quite successfully is using something like ChatGPT to say, I want to improve the travel of my central time zone teams. Write me the constraints for that. And amazingly enough, a lot of times it does very well. The challenge is if it's off a little bit on one constraint and we don't notice it, then we're solving the wrong problem. But when it comes to quantum computing, it's hard to say. I mean, there's a lot of claims out there that these are going to make all these NP-hard problems more tractable, and there are use cases out there or examples where they've solved very small specialized problems with it. But it's not something that we were really concerned about at this point. But maybe I'm wrong. Yeah.
How much variance do you need to inject year after year? I mean, you might have a really good schedule, but you can't just run the same schedule again next year. So what are those constraints between years? Yeah, well, a lot of times, I mean, so if you think about a professional league, there's way too many things that change. The arena availability changes, the TV networks change, the good teams change, and so on. When you get to, maybe something like NCAA, a non-revenue sport, a lot of times what teams have done in the past, or leagues have done in the past, is they'll just take last year's schedule. If it's a pure round robin, they'll flip it and they have this year's schedule. But now with conferences expanding, you can't do that with most of them because they don't play everybody anymore. Like when you had 12-team conferences and they played a pure single round robin, you could do that. But I can't think of a case where we try to artificially inject any kind of diversity into the schedule because we feel it looks too much like a previous year. But yeah. Yeah.
Hi, thank you. Could this be used in different sports? Like, for example, in tennis, finding an optimal schedule for juniors and even pro players is right now it's done manually. So just wondering if this is...
You mean for an individual player to plan out their tournaments?
Right. So right now we look at pro players. Hello. Yeah. We look at pro players' schedules when they were like 14 or 16, and then that way we can see what their schedules were at that age.
To a degree, I mean, I think there are scheduling and these routing problems everywhere. I mean, I think the one thing that makes these league scheduling problems, if I think about it in terms of a routing problem, like if the Charlotte Hornets are playing the Los Angeles Lakers, like, well, they've got to play, if you view Charlotte as a truck that's going to have to play that trip, well, they can only play the Lakers when the Lakers are at home, right? And so when we get to sort of these individual scheduling problems, and we have talked to some of the Grand Slams about like their TV scheduling and things like that, I think when it comes to an individual player, I mean, I think a lot of the techniques maybe become simpler if I'm thinking about it the right way. But tennis is a sport near and dear to my heart, so maybe we can talk afterwards.
We are unfortunately out of time, but please join me in giving a round of applause for Dr. Chris Garth.
Thanks.